Here's a little bit about double angle formulas. It's a pretty easy consequence of the sum formulas. So I'll just lay it out pretty quickly and we'll get most of our understanding of this through practice. So I'd like to know if there's some nice formula about the sine of double of an angle. And we looked in this latest incarnation of the class, we looked at some explicit examples to convince ourselves that it's definitely not 2 sine theta. It's really important to know that it's not just 2 sine theta. But what is it? Well, it's just the sine of theta plus theta. We've got a very general formula for the sine of the sum of two angles, and we can just put that in. And so that's going to be sine theta cosine theta plus cosine theta sine theta. Oh, that looks familiar. And that simplifies. It's just going to be 2 times sine theta cosine theta. Notice that it has the subconscious formula, the incorrect oversimplified formula in it, but it's got a very major modification. 2 sine theta cosine theta. That shows up a lot in various mathematical places. So that's the formula for sine of 2 theta. We'll do a reality check on that in a minute, but I want to talk about the other formulas. Cosine 2 theta. Okay, that's just cosine of theta plus theta. Okay, again, if you look at some explicit angles, you can see that that is really not 2 cosine theta, and we'll see the real answers in a minute for a particular pair of angles. But we know what it is. It's cosine theta minus sine theta sine theta. And that doesn't simplify quite as nicely, but we can just tidy it up a little bit. Cosine squared theta minus sine squared theta. Oops, that's not what I meant to do. And this is really important. This looks a lot like cosine squared plus sine squared, but that's equal to 1. That's something that's always the same number. That's a really basic Pythagorean identity. This now turns out to be another interesting quantity, but it's not always equal to 1. It's not always equal to any fixed number. It's just another way to express cosine of 2 theta. So both of these formulas say that if you know sine theta and cosine theta, you know the sine and cosine of double those angles automatically without having to calculate them directly. Okay, what about tangent? Might as well do it. We get something pretty interesting. Theta, just kidding. Tan theta plus theta, and that's supposed to be a plus. Okay, and here we get this fraction guy, right? This is tan theta plus tan theta over 1 minus tan theta times tan theta. Really just putting in theta for both slots of this formula. The book uses u instead of theta, but I like to emphasize that it's usually going to be some sort of thing we could interpret as an angle. Okay, so you get 2 tan theta on the top, which is what a lot of people are going to guess is tan 2 theta. If you just try to sneak that 2 out, and again, a major modification. It's divided by this 1 minus tan squared theta. Oh, notice the cosine here. This isn't even trying to be 2 cosine theta. Cosine really doesn't even try to look like the sort of simplified linear function type of guess. Okay, so those are cool formulas to have. Let's make things a little more concrete by just plugging in some numbers, okay? Sine of 2 times pi over 4. So this is pretty easy to calculate directly, okay? But let's hold off on it a sec. Let's go ahead and use this formula, and then we'll double check, because we really know the answer, okay? So this is supposed to be 2 sine pi, just kidding, over 4 cosine pi over 4. Okay, so 2 times root 2 over 2. Oh, and that's also root 2 over 2 from our unit circle. So root 2 times root 2 on the top is 2, times another 2 is 4. All over 4, you get 1. Oh, totally. 2 times pi over 4 is pi over 2, and the sine of pi over 2 should be 1. So this double checks that this is not crazy. And it's kind of cool how it all fits together. This sort of has to work, but it's also a little bit magical. Now what about the cosine? Okay, cosine of 2 times pi over 4. Let's do it in the opposite order now. 2 times pi over 4 is pi over 2. Cosine of pi over 2, wait for it, think about it, it's 0. So there's got to be some sort of cancellation. If I'm going to be taking the ingredients of cosine theta, cosine pi over 4, like this guy, and sine pi over 4, and they're going to give me 0, there's got to be a cancellation somewhere. And that's what this magic minus sign is going to do for us. We're going to take cosine squared of pi over 4 minus sine squared of pi over 4. But we just realized that those are the same number. That's root 2, if we want to make it really explicit. Just, let me get there. root 2 over 2 squared minus, oh, same thing, we're just going to copy and paste. Okay. That happens to be 1/2 minus 1/2, but it's just something minus itself. It's 0, which is what it's supposed to be. Now, this is an even more interesting one. Tan of 2 times pi over 4. Okay, well, our naive guess, which is totally wrong, would be 2 times tan pi over 4, which would be 2 times 1 is 2. Okay, well, the real thing has that as part of it, but has a very, very, very important modification. And this is where we discover why it's really important that that's in a denominator. Okay, so that's 2 times 1 over 1 minus, well, tan pi over 4 is 1. Tan squared is still 1. Over 1 minus 1. Uh-oh. This is undefined. Is that a bad thing? No, it's not a bad thing, because 2 times pi over 4 is pi over 2. What were we trying to calculate? We were trying to calculate the slope of a vertical angle, an angle that goes straight vertical, a line that's totally vertical. This is supposed to be undefined. I'm deaf. And so it's totally making sense that this has to happen. So the bottom going to 0 was actually a really good thing. It gives us the only accurate way that this could be represented. Okay, that's enough for this video.